Good morning, everyone. Thank you for being here. It's my honor today to introduce Dr. John Ioannidis, a leading figure in the fields of epidemiology, medicine, and public health. He's widely regarded as one of the most influential researchers of his generation, with a career that spans decades of groundbreaking work in the analysis of medical research, methodologies, epidemiology, and statistical science. So thank you for being here. Dr. Ioannidis began his academic journey at the University of Athens, where he earned his MD degree, ranking top of his class. Then he pursued a doctorate in science and biopathology, and then he moved over here to the US. He completed his residency in internal medicine here at Harvard, and then a fellowship in infectious disease at Tufts. Following that, he held various positions at the NIH, Johns Hopkins, and Tufts. And following that, he moved to Stanford. He moved to Stanford in 2010, and initially he was the director of the C.F. Romberg Chair at Stanford Prevention Research Center, and he became a professor of medicine, epidemiology and public health, biomedical data science, health research and policy, and he launched a PhD degree program in epidemiology and clinical research, and the master's in science and program in community health and prevention research. He then launched, and he's currently the co-director of the Meta Research Innovation Center, which is internationally recognized. It's like a hub of a large international network of researchers interested in studying and improving research practices. Dr. Ioannidis has held numerous prestigious positions throughout his career, including serving as executive board in the National Cancer Institute and the NIH. He also served as the president of the American Association of American Physicians from 2023 and 2024. He was part of the editorial board members of well-known scientific journals, as the Public Library of Science of Medicine, Biology, The Lancet, Annals of Internal Medicine, and all the list just keeps going on. He was recognized with numerous awards, including the European Award of Excellence in Clinical Science, the Chanchalani Global Health Award, and the Albert Steinberg Medal, among many others. He became honorary titles and doctorates at Rotterdam, University of Rotterdam, University of Athens, and Edinburgh. The Atlantic selected Dr. Ioannidis as the Brave Thinker Scientist in 2010. He may be one of the most influential scientists alive. Dr. Ioannidis has published more than 1,300 peer-reviewed articles. His work earns him around 3,000 to 6,000 citations per month, with some estimating that he's one of the top 6 most cited researchers globally. He has an H index, which measures both the productivity and citation impact of 270, also ranked high, one of the highest in the world. His seminal paper that changed things on how we look at research, and it's very well known, is why most published research findings are false. And I think that's what revolutionized all research that we know today. He challenged the validity of many commonly accepted research findings and called attention to importance of methodological rigor in medical science. This paper alone had profound impact on the scientific community. It's the most accessed article in history of Public Library of Science, with over 3.2 million hits, and the most used technical article in Mendeley. Dr. Ioannidis' research continues to shape the fields of epidemiology, biostatistics, and evidence-based medicine. So we are privileged to have you here today, and looking forward for your talk. Thank you.
I just want to say 2 things about John. I think we know each other. I'm not going to give up our age, but more than 25 years. And the first thing I remember when I met John was like, he cannot be the John Ioannidis. Like, people at that point, he was not as famous as he is now, but people would think that the city that we met in Ioannina was named after him. And he was so kind, so simple, open door policy, and you would be amazed of how kind and gentle he was. At the same time, John is, like a fighter when it comes to truth, his beliefs, and, when he wants to make a point. I still remember, like the day of us talking about, that amazing innovation that you can take a drop of blood and then you can, make it to a test, and, it was big in the news. And then 3 months later, there is a letter, and 2 years later, there is a big scam of Theranos collapsing, as this was probably a completely a thing that couldn't be done, and they were faking the data. And I remember John saying, "Can you do it? Is it reliable?" And a few months later, everything collapsed. The last thing I want to say about John is a man of great and amazing talents. He told me yesterday that he has written number 10 of his book of poetry and novel, and he composes music. And I don't know where he finds the time to do all these amazing things, but you will find him shooting balls, swimming, doing, fun stuff. So, John, welcome. We are honored that you are here.
Thank you for the very kind invitation and the warm hospitality and all these excessive praise, which clearly cannot match with what I'm going to discuss today. So reproducible and useful biomedical research. This is something that has been tantalizing for a while now. And I want to start with some preemptive comments. First of all, science is the best thing that can happen to humans. All the budget of society should go to science. Well, not all, but we should continue to support science rigorously. Most scientific research done to date, however, has used non-reproducible, suboptimal research practices. Science is becoming more massive, more complex. We have more than 40 million people who have authored scientific papers. We have more than 200 million papers already. They're increasing at a rate of more than 7 million per year. Most of them are advertisements. They're more like, trust me, I have done this work, this research has been done, but the raw data, the experimental materials, the algorithms, they're not shared. So the question is, can we do better? Not whether we have a small or big problem, but can we do better? The question is, who is it who should try to do better? Because maps of science suggest that there's not one science, there's literally thousands of scientific disciplines. And even though all of us, we say and we claim that we use the scientific method, our research practices vary substantially across this universe. This is a map of science that I have drawn with my colleague, Kevin Boyack. Each little dot that you see there is one discipline. And the practices, the way that people expect that a good scientist should behave might differ from one dot to the next. Now, that universe is not everything that is done or contemplated or speculated or argued or funded or sponsored around science. Much of the scientific universe may be unpublished dark matter and also dark energy. If you think about the real universe, 5% is ordinary matter, 27% is dark matter, and 68% is dark energy. And I think something similar may be the case also for the scientific universe. In fact, even though I believe that disciplines on average, most of them improve over time, if single fields improve over time, the total universe may still get worse if the dark matter and dark energy increases, and or if the least reproducible fields grow at a faster pace. So if you have some scientists who are very rigorous and very careful and focus on getting credible results, and they improve their practices, and that happens in several scientific fields, but then you have many, many others who are growing at a very much faster pace, then the average paper out there, if you were to randomly select a paper, might actually be worse. We have many reasons to believe that the scientific literature is infested more massively by highly problematic papers. Some of them are clearly just fake. For example, multiple editors have tried to assess how much of the literature is fraudulent. Wiley announced that 1 out of 7 papers that were submitted to their journals could be detected to have been created by an LLM, apparently a fake paper. And other efforts that are more detailed, like this one that happened in the journal Anesthesia, which is a very respectable journal. One of the editors, John Carlisle, decided to ask for the raw data of the randomized trial submitted to his journal, he concluded that about 30 to 40% of randomized trials submitted to the journal were so messed up that either people had no clue what they were doing or they must have been fraudulent. So he called these trials zombie trials. And I published that editorial. It came out on a Halloween day, very appropriately. I estimated if what he had found in a very respectable journal was true for other journals across medicine, then we have about 500,000, perhaps even 1 million randomized trials that are zombies that circulate among us. Leaving aside the completely fraudulent, which hopefully is still not the majority, although it's growing, we have the problematic or the questionable research practices that probably are highly prevalent and are probably affecting the large majority of scientific productivity. There's some common features. One common feature is that people chase statistical significance. They want to convince themselves and others and funders that they have something significant to say. Statistical significance has become a boring nuisance. We noticed that many years ago when we pretty much text mined the entire PubMed, both abstracts and full text articles, and 96% of the time when p-values were used, there were statistically significant results claimed. So this has very little discriminating ability. More in-depth assessments suggest that much of that significance is really not very fair. We have surveys of biostatisticians, for example, who have been asked, how do you interact with principal investigators? And they have admitted that in a very large share of situations, they're under pressure to develop this type of significant results by means that I would characterize as not appropriate. The vast majority of research does not even involve methodologists and statisticians. So you have the researcher who can really game the potential of their work and eventually find some result, perhaps even fooling their own selves. That seems to be interesting, but actually it's just an iterative process of finding significant results. Medicine may actually be better than other fields. We have the capacity now to examine multiple fields, like in this paper where we looked at medicine, environmental science, psychology, and economics. When you have large-scale evidence synthesis with meta-analysis, for example, we could use 67,000 meta-analysis from Cochrane for medicine. We see patterns that are compatible with very strong publication selection bias in all of these fields, perhaps worse in the other fields compared to medicine. And this has been attacked as a notion from different angles. This is another way to look at it, looking at the distribution of effects and p-values in a whole scientific body like economics. Economics seems to be worse than medicine, with the vast majority of their papers affected by this selective reporting. We have seen some improvement in some fields. For example, this is an in-depth assessment that we did in reproductive medicine, where we saw that there were fewer significant results over time, especially for some types of designs, for example, for randomized trials. In the past, one might say, well, this is not good news. I would say this is good news. It means that probably there's more acceptance for results that may not be outright extreme in order to be significant. Or perhaps we have also inverse publication reporting bias. This is a few examples of why in some settings, scientists and sponsors may be incentivized and may prefer to have non-significant results reported. For example, studies of toxicity and harms of interventions. The incentive would be towards reporting non-significant signals. Non-inferiority studies that are becoming more common in regulatory settings. Increasingly, we do not try to prove that a new drug or biologic or device or some intervention is better, but it's just not much worse compared to what we already have. Or people like me who want to prove that everything is wrong. I have every reason to be biased to get non-significant results when I try to run some replication study. So I may be highly biased in that regard, and we may be seeing more of that. Having the benefit of all these millions of papers that are floating around, we also have the benefit of mapping bias across different scientific fields. For example, in this paper in PNAS, along with Dan Fanelli and Rodrigo Costas, we looked at about 250,000 studies published across every scientific field. The main 20 scientific fields across science. And using meta-analysis from these fields, we tried to say, if you have any of these about 20 different biases, what type of pattern of results would you expect to see? Now, if you see it in a single topic, in a single meta-analysis, you can not say much. But if you see it across many tens, hundreds, thousands of meta-analyses, then that means that probably this signal is compatible with the presence of that particular bias. What we found is that biases are ubiquitous. They happen across almost any scientific field, but some fields have more of one type of bias and some other fields have more of another. For example, if you compare in broad strokes, physical sciences against biological, biomedical, and social sciences, when it comes to small study effects, small studies giving exaggerated results and extreme findings, very common in social sciences because most of the studies are pretty small. Also common, very common in biomedical sciences, in many fields, including surgery and orthopedics. Most of the studies are pretty small. Not common in physical sciences. Well, most physical sciences don't have a problem with small data sets. They have CERN that can generate gigabytes of data sets in split seconds. They have these telescopes that collect information. That the problem is what exactly to tap into that vast information treasure. Other biases may be common, conversely, in physics or perhaps more in biomedicine or less in biomedicine. So we need to study what are the hallmarks of bias in each field and in each subfield and each subdomain in order to try to understand what is wrong and how to make progress. There's a lot of people who want to help in that regard. And this is one example of a paper that we published 7 years ago, multidisciplinary people coming from very different scientific fields, all agreeing that what we need is more reproducible science. The paper has been cited many, many thousands of times from domains that really do not communicate with each other when it comes to what they do, other than the fact that they have a common quest of improving the rigor and the reproducibility of the research practices. So how do we move from having all that universe of not so credible results to making results more true? We have lots of options. We have lots of opportunities. Research is not a one-step, one-result process. It is a multi-step, integrative type of an iterative process that has lots of opportunities for things to go wrong, but also each of these steps is an opportunity also for improving our standards and improving our practices. Who would do that and who would take the lead? That's also something that we need to answer. Is it scientists? Is it like a grassroots movement that we need to ask for? Or for clinical science, clinical research, is it clinical researchers, clinicians who should start that revolution? Is it journals? Is it publishers? Is it institutions? Is it regulatory agencies? Any sort of sponsor? Should it be eventually the general public that is affected and is expecting to see science improve their lives and save their lives? This is a question that has been posed for a while now, and you see efforts that start from different angles and from different perspectives and from different stakeholders. If the intentions are good, well-intentioned efforts, I think, are always welcome, but there's also the problem that we may end up with some anarchy on who is doing what and who is proposing what, and also why are they proposing whatever they're proposing. I don't think that all the stakeholders are well-intentioned. I think that the major anxiety that we have recently, especially in the US, is how much of that is really well-intentioned thinking versus retaliation versus retribution, who is trying to get the upper hand on what? Is it more like a power game? And are we really interested in science or something that is not really so relevant to science? Science may or may not be useful at first sight. I love science that you have no clue why you're doing it. You have no clue why and how it may be applied. Completely blue sky, basic research is wonderful. But when it comes to some types of scientific investigation, in particular clinical research, I think we need to aim to be useful, because this is really deliverables that we're talking about. And these deliverables are people with better outcomes in terms of their lives, their quality of life, their capacity, their function, their everyday experience, and eventually whether they're alive or dead. So here's 8 features that I believe would be important to consider as features that may herald that research is useful. Number one, we need to have a problem to solve. A lot of clinical research, unfortunately, does not try to solve a problem, but tries to create a problem that then there will be a market for that problem. And I think that this is not a good approach. Context placement, we need to know what has already been done rather than start from, well, we'll just add another study. We add another study, what is the information gain? How much is the entropy of the system going to change by adding that new experiment, that new trial on top of what we already know? Pragmatism, does it reflect real life? Patient-centeredness, have we asked patients what they really care about rather than what the clinician or the researcher cares about? Value for money, especially with limited budgets, are we investing our resources properly to what may have a larger payoff? Feasibility, can it be done? A lot of trials in surgical disciplines get abandoned because there's not enough patients to recruit eventually. And finally, transparency, are the methods, the data, and the analysis verifiable and unbiased? I think that if you decide to read an average paper, probably it will score 1 or 2 out of these 8 features. If you decide to read a paper from New England Journal of Medicine or Lancet or BMJ, maybe it will go up to 2 or 3 on average. A few will have 7 or 8 out of the 8 features, but these are really rarities. Across the board, most of clinical evidence is not really that good. We can look at clinical evidence in large scale, for example, through the Cochrane database. This is one example where we looked at 1,400 systematic reviews, and only 13.5% of them had high quality of evidence. If you ask for significant results, favorable interpretation of the intervention, along with high quality of evidence, only 25 out of the 1394, less than 2% of clinical topics had this desirable constellation. We also have to admit that for most clinical questions, we do not have the benefit to go all the way to test them with mega trials. This is one assessment where we try to see how many mega trials are out there if you exclude vaccines and a couple of other topics where mega trials may be done on a population basis. We only found about 150 mega trials. And these mega trials do not necessarily agree with smaller trials, and most of the time they give non-significant results. Now, of course, if you decide to go all the way to run a mega trial with 10,000 plus participants, probably there's some good reason to believe that there's a residual uncertainty to go that far. And I think that for most questions, we cannot go that far. We have to be happy with small trials, with small constellations of evidence, but then we have to ask if this is enough and if this is credible enough. Where does reproducibility come into play into this situation? Everybody's talking about reproducibility. The use of the term reproducibility of results, for example, is growing exponentially, but there's different meanings of reproducibility and different goals that people have when they say, I want more reproducible research. For example, you can think of reproducibility of methods, the ability to understand what was done and repeat what was done. Reproducibility of results, the ability to do another study if you can understand the methods of the first study and hope that the results will be congruent in the second study versus the third one. And reproducibility of inferences, where you have experts, people who know, and perhaps also non-experts, but let's say experts who try to interpret the evidence, and they do not necessarily reach the same conclusions or the same action plan or the same guidelines. Improvements are possible to a different extent in these 3 dimensions. For reproducibility of methods, I think that we should be able to understand what has been done in a piece of work, of scientific work. Some fields have taken that seriously, but these are not necessarily the fields that produce many papers. Reproducibility of results remains unknown for most fields because replication is seen as a Me Too exercise. The new NIH leadership says that there will be more investment on replication. I would have to wait to see how that gets implemented. But most fields feel that replication so far, why do you waste your time? If you get a negative result, you're back to square zero. What are you going to say? I did this, I thought I found something, but now I understand that I found nothing. And reproducibility of inferences, I would wonder whether it is even possible and worthwhile to improve? Do we need to streamline everyone's opinion to be the same? Along with Howard Bauchner, I have argued that interpretation of medical evidence is almost unavoidably very subjective. And sometimes the best that you can hope is to map why it is so subjective and what are the incentives, what are the conflicts, why do people reach different conclusions? Perhaps they work in different areas of medicine with different priorities, with different conflicts, with different needs. We also have a number of exercises that have been performed in different biomedical fields where the most interesting aspect of reproducibility replication attempts is not so much our inability to replicate results. Yes, when we do get the experiments running, only about 20% of them replicate, like in the case of Reproducibility Project Cancer Biology. The most interesting part is that most experiments published in the creme de la creme journals cannot even get started to be reproduced. From 193 experiments, eventually only 50 could be done. So the other 143 could not even be done, even though people tried to reach out to the investigators, ask them thoroughly, well, how did you do this? What exactly happened here? For those that were done, it took on average 197 weeks from designing that replication effort to publishing it. And actually eLife was waiting to publish these results. They had promised to publish them. So it was not that they lost time in publication. So you can imagine the average graduate student, PhD student who goes to the lab and their advisor says, well, try to do this experiment that was published last year in Nature just to get started. And once you can get your hands wet, then you can start doing your own work. And that experiment would take 197 weeks just to get something that was already published in Nature. Some people feel uneasy about raising these issues. They feel that science is being attacked, their reputation is being attacked. Are you telling that I'm wrong? I'm happy to be told that I'm wrong because I say that most research is wrong. So my research probably is also wrong, beware. But most people don't like that. And I think that this leads to reproducibility wars. And we have to be sure that we disintegrate and disengage reputational threats and emotional threats versus science, science that really matters. There's also resistance to refutation with persistence of contradicted claims in the literature. Even after many randomized trials show absolutely nothing, people will continue to cite that beta-carotene is an effective chemopreventive effort. In psychology, that had a lot of soul searching and did all these multiple replication efforts, many of their creme de la creme findings got nowhere, it could not be repeated, but they still get highly cited. And we've seen that in epidemiology, in medicine, in many other fields. Out of the multiple research practices that we have that could improve the situation, it's hard to pick one that would be the silver bullet. Large-scale collaboration helps, teamwork, cross-checking of results, adoption of more applications, registration, sharing, reproducibility checks, containment of conflicts at the level of sponsors and authors, more appropriate statistics, standardizing definitions, analysis, more stringent thresholds of claiming discoveries or successes, improving study design standards, improving peer review reporting and dissemination of research, and better training of all of us in scientific methods and statistical methods and statistical literacy. The question is, who should do each of that? Because I think that we sometimes have a notion that, oh, you're the one who needs to take action. For example, principal investigators should share their data. Well, we try to reach out to the principal investigators of the most highly cited papers across each scientific field. And these are the results from psychology and psychiatry that we have published, but we've seen similar patterns in other fields. The most common reason that people did not share the results is that the principal investigators did not control the results. They did not control the data sets. They had no access to the data sets. The sponsor, a company, had run the data collection, had run the analysis, had sent them the paper. I hope they did take a look at the paper before putting their name on, but they don't really have control of the data. Then journals and publishers are trying to improve the situation. For example, they say, please have data sharing statements, and all major journals have data sharing statements. So we tried to look at 500 trials. Yes, most had data sharing statements. About half said that they will place some individual level data sometime in the future. About 20%, they would put it in a specific repository. About 5% would be clearly individual participant data in a repository, and only 2 out of 500 trials had the raw data right now. You could look at them today if you wanted to have access to them. Many of them had embargoes. We published that follow-up in JAMA, where we try to see what happens with embargoes. Some of them are lifted, some of them are protracted. In some other cases, nobody's telling what is going to happen eventually. Some journals are more strict. For example, BMJ and PLOS Medicine are asking not for a promise or for a description of what one wants to do, but if you publish with us, you need to promise that the raw data will be available. So we reached out to trialists who had published in these 2 journals, and we said we want to rerun the analysis, a little bit like an IRS audit, but 46% of them did send their data sets, and when we rerun them, we got pretty much the same results. So in an environment where there is trust, where there is focus on sharing and transparency, probably one can trust what they see. Some other fields are moving towards default sharing. For example, in genomics, we published that paper in Science 6 years ago, arguing that everything that is publicly funded with genomic focus should be immediately shared with everyone. And we have seen some improvement. We have seen, for example, data sharing in this large-scale text mining of the entire open access biomedical literature. It has gone up from close to 0% 20 years ago to about 20% currently. We have gone from 0% for code sharing to about 5%. We've gone from 0% on protocol registration to about 7%. We have placeholders for conflicts of interest disclosures and for funding disclosures all the time. I don't know if they're complete. I don't know if they're accurate. I don't know if they're honest, but at least there's a placeholder. And there's more people who acknowledge that what they do is replication. They're not afraid to say so. The adoption of these practices is not the same within the universe of science. So you see that data sharing has color in some scientific fields. A subset of these fields has been sharing code as well. A very different subset is registering protocols. Typically it's randomized trials, but these are not really the studies that share code or share data sets. So if you want all of that, it's very unlikely that one would get it. With new challenges, we need even more transparency. As our computational methods are becoming more complex, you need new types of efforts to make sure that these are not black boxes. We published some recommendations 8 years ago in Science. I think they're growing old because there's a trade-off between transparency and complexity. If you have a plain regression to report, you just need the coefficients and the constant, and that would be transparent enough. If you have deep neural networks, you can still be transparent. We published these recommendations in Nature a few years ago, where even in a very complex environment of deep neural network artificial intelligence, you can make the process very transparent and reproducible. With LLMs, this may no longer necessarily be the case because LLMs by definition are not reproducible. They train on a data set that is different tonight compared to what it is going to be tomorrow. And there's new challenges, understanding their performance as they become kind of a gold standard, spreading misinformation, creating new types of inequalities and societal impact, changing the scientific ecosystem, who's going to be the researcher, who's going to be having the idea, who's going to be running what, ethical issues and broader issues. So will we get more reproducible research if we do some of that or all of that? That's what we hope. And this is one example of one paper published very prominently in Nature Human Behavior, claiming that there's high replicability of newly discovered social behavioral findings if the research can be registered and the process is rigorous. Very high success rate to reproduce these results, 90% plus. The problem is that a few months later, that specific paper got retracted because even though it claimed it had been pre-registered, it was not pre-registered. And even though it promised to have some rigorous practices, that's not really actually what had happened. So I want to end with a note of caution that non-evidence-based solutions may even be harmful. There's lots of people who want to be saviors of the world. They believe that research is in dismal shape and I will save it by doing this or by putting forth some crazy idea. We have to be very careful because things can be worse than they are, and perhaps they're not that bad as they could be. Research practice indicators are surrogates. All that I mentioned, sharing, replication, registration, transparency, they're surrogates. They're not the end goal of research. The end goal of research, especially medical research, is to help people, to save lives, improve life expectancy, have better outcomes, have better function, have better quality of life. It's not about satisfying the Ioannidis checklist of 55 research practices that you need to follow to torture yourself. And I think that we have to be careful because we do run the risk of being overwhelmed by non-credible research. This is an in silico universe of science that I built with David Grimes with 11 equations. Basically, it constructs a universe where there's diligent scientists, there's sloppy scientists, and there's fraudulent scientists. How many are the fraudulent scientists? Well, let's say maybe 1%, 2%, very few. How many are the sloppy? Depends on who you ask. If you ask, are you sloppy? No. If you ask, are people in your environment sloppy? The answer is always yes. But let's say that the majority are diligent and we just reward everyone for what they managed to achieve, what they managed to publish. We give them funding if they manage to publish. The sloppy and the diligent, you don't need differential equations to see this, will take control. Why? Because they have a competitive evolutionary advantage. They can publish with less work, with less effort, if you're completely fraudulent, with no effort. So we need to find ways to reward good practices or penalize poor practices. The balance between reward and penalty needs to be debated. Who is going to do that? To a large extent, it's still going to be us. It's us reviewing other peers. And how to do this is not an easy job. It's not a perfect job. It's not an accurate job. For those who are interested, please join us in the International Congress on Peer Review and Scientific Publication. I'm the director of the Congress happening in Chicago, along with Metrics, BMJ, and JAMA. To conclude, there's a lot of discussion and there's a lot of anxiety and a lot of uncertainty surrounding how to improve research practices. It is just getting worse. Unfortunately, it's also getting polarized and even extreme at times. There may be even a ceiling on how reproducible and useful research can be. Perfection is unattainable, but improvements are possible. Reproducibility indicators are surrogates. What matters in research, science, and its positive impact is far more complex. And there are new stakeholders and new ways of publishing science or of disseminating science or understanding science or appraising science or funding science. And they may change fundamental notions about what the scientific record is and what we should be aiming for. So both a time of opportunity, but also a time of threat, and you can see it whichever way you prefer. Thank you so much.
Thank you, John. I'm not sure if there are any questions.
I have a question, if I could.
Yes, go ahead.
Thank you very much, John. I really appreciate our discussion last night. I just wonder if you could, at the risk of being, I don't know, a little bit controversial, you're talking to orthopedic surgeons. So in 2003, I think McGlynn wrote an article in the New England Journal of Medicine about which specialties had the best evidence for the treatment that they applied. And orthopedics was not on that list. Can you comment briefly about your overview of the quality of research and the evidence used for clinical care, perhaps in different specialties, who seems to be the highest, the most rigorous? And I don't know, maybe we also don't make your list here, but maybe in the context of us orthopedic surgeons in this meeting.
Interesting question. And I don't think that I will come up with a clear winner and a clear loser because it's multiple factors that one has to take into account. For example, if you say which specialty has the larger number of randomized trials and the largest cumulative evidence, probably on the top you will see cardiology and oncology. But at the same time, both of these specialties have very strong infiltration by big pharma and big device. This means that they have a specific signature of their evidence. Maybe it scores very well on most of our checklists and risk of bias tools. It will score very nicely. Why? Well, if you have a sponsor who needs to spend $500 million to develop a new drug or a new intervention, and they know that they will be scored based on these 10 items, they will clearly take care of that. It's just 1% of their budget to make sure that we will satisfy the checklist. But then the questions that are asked and the research agenda that is created, and whether these are really the most relevant and most pragmatic and most patient-centered, and whether they do make a difference eventually, that's a different story. So seemingly good evidence, but not necessarily what one would expect from all that investment. Most surgical specialties, not just orthopedics, tend to score very poorly in the amount of evidence, number of randomized trials, and especially large-scale randomized trials, multi-center trials, carefully designed and carefully done and translatable and easy to apply to many populations. Not just orthopedic surgery. This has been a concern across surgery, but there have been many efforts to change that over time. So we do see more being done, and probably more pragmatic and more relevant. I think that orthopedics is not necessarily worse compared to other surgical specialties in that regard. Some surgical specialties probably have an advantage because they also team with some non-surgical specialties that have more of a tradition of evidence-based. For example, cardiovascular surgery has that connection with cardiology that has the pattern of having large randomized trials. But even then, a couple of days ago, we published a paper in Journal of Clinical Epidemiology with 73 meta-analysis covering the entire field of adult cardiac surgery. Our conclusion was that if you exclude the early big successes, CABG, aortic stenosis, a few more, nothing seems to have made a difference in terms of mortality. Maybe there's some other outcomes that have been improved, but really all these hundreds and hundreds of trials that have been done have not really improved mortality outcomes, which is what eventually would matter. For orthopedics, another challenge is what exactly is the outcomes that one should prioritize? Because in the vast majority of cases, it's not going to be mortality like cardiovascular surgery. It's going to be outcomes that are more functional, that relate to some of them may be complications and need for reoperation, but others would be more related to functionality and what people do. Some domains are even more difficult to study in that regard. If you go to sports medicine and what really is it that we want to do? So I'm not going to tell you what that would be. You probably know far better than I might speculate. But I bet that what is important may vary from every single patient to the next. If you have orthopedic sports medicine where you're dealing with elite athletes, their goals and their perspectives and what makes a difference for them is going to be very different compared to an average citizen. I'm not sure I gave a good answer, but don't blame yourselves because it's not a unidimensional scale that one has to appraise what is being done.
Thank you.
Hi, brilliant talk. I really wanted to come and listen to you today. So I wanted to talk about the transparency, and often in clinical papers, you've seen a method, univariate analysis, then a jump to multivariate analysis. And often, even though they sometimes share the data, the model development isn't really clear. And I wanted to get your opinions and views on how we can improve the transparency with that, especially with the use of large language models, which allow people who aren't computationally trained now to get the statistical models, which they can just fill in patient data. To use, someone can get a model, fill in patient data, but they haven't really explained how they develop that model to see if it's a valid model at all. And how can we make that more transparent so that we can follow the arc of the paper? That's my question.
Interesting question. So I think if one has a clear idea of what they aim to do, then there should be a protocol that should be posted, time-stamped, available for everyone to see ahead of doing the research, ahead of collecting the data, ahead of running the analysis. Everyone can see that this is what I had in mind, and this is what I plan to do. There can be deviations, and the deviations can be justified. That I came across this, and I thought that was the best response to modify the protocol in that regard. Now, we have more protocols. As I showed you across medicine, we went from 0% to about 7, 8, maybe 9% currently of studies having registered protocols. The vast majority do not. Even those who have protocols, usually the protocols are not detailed enough when it comes to the statistical analysis plan. So we have also the possibility to timestamp and post a statistical analysis plan. And we see more of that. It's still less than 1%. It's mostly about randomized trials, but it's still only for a subset of randomized trials that this is done. Then you are very explicit about how am I going to run the analysis? What is going to be the regression model? Why am I choosing these variables? What might be my sensitivity options? And everybody knows that this is what is expected to happen. In the absence of that, I believe we just have to be honest. A lot of research is exploratory, and there's nothing wrong with that. I would just say, just be forward, honest in that I run an analysis that is exploratory. And then you can explain why I chose this model or why I didn't choose that other one. In principle, for most analysis, there's so many options, especially when we talk about regression analysis. I have coined the term vibration of effects because you can think of all the possible ways that you can run a regression. For example, depending on what you want to adjust, if you have two choices to include the variable or not, you have 2 raised to the number of variables that you can consider. You have 20 variables, then you have 2 to the 20th power, which is 1 million ways to run the analysis. And these results may be completely different depending on which one of the 1 million analysis you choose. I have even proposed that one should show the map of these 1 million analysis to be able to tell whether there is consistency in and robustness in the result, or there's some factors that sometimes yield a result that is suggesting that this intervention helps, and some other combinations of analytical choices lead to a completely opposite conclusion. So transparency may just mean honesty. I'm exploring. Exploring is fine. That means that someone else now needs to come and try to see if by reproducing the exploration, they get the same result.
Great talk. Thank you. Early on in your presentation, you talked about statistical significance and all the well-known problems, that's created. But it seems for decades now, there's been a lot of good papers and information out there that this is sort of a paradigm that's almost creating part of this problem. And I think we've seen a lot of really smart people over the years try to fix it, yet we're still like in its grasp. How do we disengage from that?
I think it's not easy to disengage. And even if you ask expert methodologists, they will have very different perspectives about that. In fact, there have been methodological wars within that space, both of reproducible research practices and even more so on statistical significance. Some of the fierce battles of methodology have been fought in that space. For example, 800 people signed a commentary in Nature about 6 years ago, arguing that statistical significance needs to be abandoned, completely abandoned. Don't say that again. And I was on the other side of that. I said, well, I don't think that we should throw the baby out with the bathwater. I think that statistical significance has some meaning, and we should take it seriously for what it means. And in some cases, it is even a good thing to have in principle, because otherwise it's going to be a free lunch situation. Anyone can publish anything and say this is important, this is wonderful, you need to do this, everyone should use that technique from now on, this is a strong risk factor. Why? What is the threshold of credibility? No, I just say so. So there's no consensus on how exactly to go about it. The common denominator, I think, is that we're dealing with flammable material, with data sets that most people are not trained on how to handle it. And now the question is, how do you make everyone a methodologist? We cannot do this. Should everyone become a statistician? No. Should we try to engage methodologists and statisticians more strategically? That might help. Where exactly, at what stage, early on, late on? For example, there's a randomized trial that says that if you involve statistical peer reviewers, papers do improve. Well, almost nothing else improves papers. Open, blind, training, in peer review, whatever, not really any concrete benefits. If you involve statistical reviewers, you improve the papers. But can you involve statistical reviewers to review 7 million papers every year? Not really. And is it a good investment to involve them late when the work is done, the research is completed, someone has submitted the full paper, or to involve them early? These are all open questions. I don't have an answer. I think that you will hear extreme positions like you should have a license to do research. Some people have published in Nature that you should have a word limit, how much you can publish every year. Like, you spend your 4,000 words, that's all for the year, wait for next year. Crazy. I think that many of these solutions will just make things far worse. I think we should not diminish creativity, innovation, maverick thinking, the ability to explore, the ability to make mistakes by putting everything into very tight statistical jackets that we don't even have agreement on which one is the best.
Good morning. Thank you for your great talk. One comment about something you said earlier. I have a very close friend. Okay, I have a very close friend who worked in clinical trials. And I was surprised about what he told me about what happened in some of these companies in terms of when recruiting patients, they have certain criteria. Sometimes they make the criteria work in order for certain studies to work. So what you said, I was like listening to it, like, wow, this makes even more sense. But more in the medical, like medication and stuff like this. My question is, and this is like an extension to what JP asked you. A simple example, I'm a shoulder surgeon. So rotator cuff. If you have a large rotator cuff tear, I'm just taking technicality, but I just want to see what you think. They say, if you do biceps SCR, it works. If you do a patch, it works. If you do, and there's a clinical study about it. If you do a partial repair, if it works. We do tendon transfer, it works. And we show it's working. How can you, if you have a patient, and you said we care about patients, we want to have good outcome, we have good outcome. How through clinical research, you can prove a methodology, this one is better than this one, or this is what the patient should have?
Well, what you described is increasingly common in many fields that have established a number of procedures, a number of interventions, a number of drugs, biologics, whatever, surgical procedures that seem to be effective. So the question is, which one is best? And that means that we need more head-to-head comparisons of these different options. Some of these head-to-head comparisons may not happen for different reasons. For drugs, the common reason is that companies do not want to have head-to-head comparisons, and also regulators are not asking that much for them. They just want to have a clean comparison against no treatment or placebo. For surgical interventions, there could be other considerations. For example, some surgeons may prefer to do one and others may prefer to do another. And perhaps if you think of volume being an important aspect of the outcomes that one gets, randomizing a surgeon who does one procedure to do one or another may not be a fair comparison. The same might be for the opposite reason for another surgeon. All of that, I think, needs to be vetted, and I cannot give an answer that would apply to every single question, but I would like to see more comparative evidence in questions that there's the perspective of getting an answer that might change the entropy of the field, might change what people do. If it's something that no matter what we get in terms of reasonably expected results is going to change what we do, then I don't think that should be prioritized. But if you think that, oh goodness, there's these 4 different techniques and these 4 different approaches, and I do believe that one of them might really be substantially better. And maybe if we do that comparison very rigorously and in a fair background, maybe we will see that. Then I think that needs to be pursued. Otherwise, it may be more important to invest on improving performance skills and volume considerations rather than go after some very minor and perhaps negligible differences on the performance of different approaches.
Thank you.
With respect to the question about chasing statistical significance and the problems that this is associated with in terms of what's published and how people go about that and all of this, do you think that adopting more Bayesian methods of analysis might actually be one way to decompress and remove some of the charge from the field, so people would not necessarily be thinking about conventional significance, but sort of degrees of supportive evidence as opposed to this, proving the null, disproving the null hypothesis. Is that? I realize even there you may still need a threshold, but is that something that just because it's like a very old and well-established way of analyzing data and it's just not being used potentially enough in applicable research?
I'm very much in favor of Bayesian approaches. I think that in most type of research questions and also clinical translation of evidence questions, they're better compared to null hypothesis significance testing. The alibi for not running Bayesian approaches in the past was that they were computationally difficult. You need to have specialized whatever. That's no longer the case for more than a couple of decades now. Lots of people are pushing for that. What have we achieved? About 2% of the literature is centered on Bayesian statistics, especially in medicine. There's some other fields that have used Bayesian approaches far more frequently. But in medicine, even though I think most, not all, methodology would say this is a wonderful idea, they haven't really managed to transform what we do. And basically, I do worry that unless people are trained to understand what they are and how they work, we may end up with the same type of problems. I mean, you said, thresholds. People say, oh, so I need a Bayes factor of 10 or 100. And everybody, instead of chasing a p-value of 0.05, they will be chasing a Bayes factor of 10. I think in most cases, kind of more stringent statistical significance or more stringent Bayes factors do make sense. For example, I was one of the co-authors in a paper where we argued that for papers that still want to use statistical significance, instead of focusing on 0.05, focus on 0.005, which immediately cuts about half of the significant results. And in Bayesian terms, it's equivalent from moving from a Bayes factor of 2.5 to a Bayes factor of 20. And I think it's not a bad idea for most of the prior literature. Moving forward, one has to vet what is the best choice, the most fit for purpose choice for analysis of a given question. And what do we want to get out of this eventually? How do we want to read the result, whatever that result might be?
That was a great lecture, John. You're really walking in the footsteps of Plato and Aristotle. So the question that I have for you is, in a world where our large academic centers are getting corporatized, how can we continue incentivizing science and the pursuit of science to keep it alive?
I think we need to do our best, and I'm open to all suggestions on how to keep enthusiasm for science and how to keep people excited about science. I mean, if you think about the life of a scientist, there's so much effort, so much time devoted, so high failure rate, and so much anxiety about the future of how am I going to sustain my work and my lab and my research agenda. So I think we need enthusiasm to start with. I think that the solutions may be different in terms of how to maintain that and how to support science in different institutions. They have very different infrastructure. They have very different resources. They have different, let's say, elasticity, to use an academic economic term, in terms of how they respond to different challenges that they meet. Some of them will just break down very easily, and others will be able to continue even with a lot of pressure. What I do see, especially for young scientists, is that we are creating an environment where we make life very difficult for them. I mean, they have to wait until their mid-40s to get their first R01. People who get a PhD, currently maybe 1% of them might end up in an academic track career. Of course, there's other places that one can do science in industry and startups, and also other positions that one could contribute important contributions. But yeah, think more about the younger generation. How do we offer them opportunities? For people who are already also physicians, clinicians, they want to be physician scientists, surgical disciplines, orthopedics with such a high load of demands on the clinical side. How do you protect some of their time, some of their ingenuity? How do they have opportunities to compete? All of that, I cannot give you an answer in 5 minutes, but there are things that have to be taken very seriously into account.
I don't know if anyone from the Zoom wants to ask something. You can see your raised hand. Feel free to jump in. I want to ask you, great talk. I want you to end on a note of enthusiasm and optimism, because I think I'm kind of not depressed, but I feel that there are a lot of challenges, and we are working hard in our own small micro practices, and we don't communicate with each other, but the challenges are overwhelming. And I want you to share your optimism of how things can change. And I feel we can end with that.
I'm all for enthusiasm. And I think, the fact that I'm here, that I still continue working on all of these topics, despite all the controversy and despite all the uncertainty and all the problems, means that I do believe that there is a future, and there's also a present. I think that a lot of good work is still done. I don't want to give the message that we have failed. It's just that we have all these 200 million papers, and even if you have 10 papers that can make a difference, that would be a major contribution to humanity. Maybe we shouldn't have our expectations so high. We should allow failure. We should say, do your best, try. It's okay to fail. It's okay not to find significant results. It's okay not to get replicated. It is okay to fail in different aspects, because it's a community effort. It's all of us who contribute. Maybe here's a lucky person who will get the Nobel Prize, but that Nobel Prize reflects also to the rest of the community that tried perhaps as hard, perhaps even harder, but that one happened to be the one who had that great success. There's lots to celebrate in science, and I don't want to leave you with a taste of disappointment. There's lots of fun and things that you cannot get through any other enterprise, I believe. I mean, people can make money, they can become famous, rock stars, but no, I would not give 2% of science for any of that. Thank you.